Hello physics students, and welcome to this screencast by yours truly, Mr. Welch. Today's screencast is going to deal with force diagrams, specifically static force diagrams. And what that means is that our objects are going to be in equilibrium. Their forces are going to be balanced. Okay, a really simple example of that, which I think we all can understand, is a block resting on some surface. The force of gravity always acts on objects, so we can automatically write that the force of gravity acts in the downward direction. And we also know that there has to be some support force from this surface on this block to oppose gravity, which is the normal force. And in this case, the normal force and the force of gravity equal each other. And there's been a little confusion with the normal force. And the best way that I can describe the normal force is just that it's a force to prevent objects from falling down, from falling straight to the ground. Just imagine if your chair got kicked out from underneath you. What would happen to you? You'd hit the ground. Just imagine if a book was resting on a table and you just slid the table off from underneath the book. The book would drop straight down. So the normal force is just a force to prevent things from falling down, from being pulled to the center of the earth by the force of gravity. Well, now let's imagine that this block is now being pushed. There's an applied force to the right here. Okay, so there's some applied force. We'll call FA. Now we want this, we know that this system we want it to be static. Okay, so if we have a book or a block that's resting on a surface and we're giving it an applied push, but it's at rest, it's static, there has to be something in this direction. And typically what we do is we assume that there is some type of frictional force acting in the opposite direction of our applied force. And I did not do a very good job of making those vectors equal today. Okay, so there's some frictional force here that is of equal magnitude to our applied force, but it's in the opposite direction. Okay, it's keeping the system in equilibrium. The forces are balanced. But how often do we really pull things perfectly horizontal? Not very often. So let's say that our force applied now is actually at some angle. It's at some angle above this horizontal. Looks a little different, right? Looks a little more complicated than what we've been dealing with. The key with force diagrams, we want to break everything into its x and y components. Okay, so we have to use all that vector stuff that we've been doing to break this up into its x and y component. So how do we do that? Well, we'll start here where this original applied force originates, where we have it originating, and we'll start with our x component, and we'll draw it so it's equal. So it's equal with the head of this applied force vector. And we're going to call this FAX. Well, now we need to connect those two. We need to connect FAX with FA here. How do we do that? We go from the head of FAX to the head. And I shouldn't have used that color. I apologize. I got too many colors here. So we'll go from FAX up to the head of our applied force, and we'll call this FAY. So now we have our force components, which together represent our original applied force. So why do we need all three of them there? Can we get rid of our applied force, our original applied force at an angle? You bet we can. We want to tell that thing to get the heck out of here. Scram, shoo, sayonara. Okay, so we're going to take that out of our force diagram. And now that looks good because we have everything in its x and y components. But does this look a little funny to you, just kind of hanging out here? Looks a little funny to me. So we're going to move this guy right over here. We're going to plop it right on top of our normal force. Okay, so F-A-Y has a new home above the normal force. So we can erase it from over here. And now that's a pretty complete free body diagram, or force diagram. We have all of our forces in the y. We have all of our forces in the x. I have a question for you now. I want you to think about it. In this situation we have here, is our normal force still of equal magnitude to our gravitational force? If this system is in equilibrium, like I said it was, is the normal force still of equal magnitude to the gravitational force? It can't be. It can't be because the forces in each direction have to be balanced. Okay, if we have two forces in the positive y direction now, and we only have one force in the negative y direction. So our normal force is now of less magnitude than our gravitational force. I hope that makes sense because we were pulling at an angle, so we had a component in our y and a component in our x. And because we had a component in the y, that normal force cannot be as much anymore. Alright? So I want to move on to a different example other than the boring old block on some surface. And I want to look at Arnold Schwarzenegger bumping himself up. Okay, so we got Arnold here, and he is just, he's just hanging around, maybe getting done doing some pull-ups. What force do we know always acts on objects? What force is acting on Arnold? Well, we know that the force of gravity is always acting on an object. Okay, so that acts in a downward direction. Now Arnold is not resting on a surface here like our block was in the previous examples. So what's preventing him from falling to the ground? What's preventing the force of gravity from pulling him towards the center of the earth? We have some forces here in Arnold's arms that are acting straight up to prevent him from falling to the floor. We can draw this even simpler than this. I mean, this is a pretty simple free body diagram. There's nothing going on in the x direction. All we have to worry about is balancing the forces in the y. Okay, because we know that Arnold's at rest. This is a static problem, so we just have to worry about balancing the forces in the y. We can make this even simpler. And I'm just going to shift over here a little bit. And we'll represent Arnold as just a black circle here. And we know that the force of gravity is acting down. And we can actually draw this as so. F of arm and F of arm. And do you see how drawing it this way makes it really easy to see that the forces are acting in the same direction? I mean, here it's still, it's relatively easy, but here they're just all in a straight line. And we've isolated Arnold here. We've literally just taken his center of mass out of this picture and placed it right here. So we know that these are the only forces acting on Arnold. Well, let's say Arnold wants to work on the outer lat a little bit. So instead of having his arms straight up in the air when he was working the lower lat, see, I'm using some Nat and Phys stuff here. Throwing that into the physics class. How about that? Well, let's say Arnold is working the outer lat now, the upper outer lat. So his arms are going to be at an angle now. And apparently Arnold got skinnier from when he had his arms straight up and down. I don't know how that happens, but in this case it does, I guess. So Arnold's arms are at some angle, theta. We know gravity is acting downward again. Now we still have forces in the arms, but we have this dang term theta. So we automatically should know that we're going to have to create some force vectors, some force vector components that make up the force in Arnold's arms. Do we all see that? Whenever we see that theta, we should know that we have to create some components. And how do we do that? Well, we use the same exact procedure as in the problem where we were pulling the block at an angle. Okay, we start here, we draw our x component over, and then we connect the heads. Okay, so we just go from the head of our x component to the head of the overall force component. So there's our force components for that force in Arnold's arm. Now I want to draw Arnold a little more simplified again. So again, we have the force of gravity acting in the downward direction. And now, different from the previous problem where his arms are straight up in the air, we actually have x components of Arnold's arms that are acting in both directions, because we know that this system is in equilibrium. And what about in the y? Well, the y is pretty similar to the last problem. I mean, we have two components again. We have two arm forces. All right? So Arnold's at rest. Everything's balanced here. Two arm forces now equal the force of gravity. These two forces cancel out. We're in equilibrium again. All of our forces are balanced. It's great. I should note that when we're drawing these force diagrams, eventually what's going to happen is we're going to find values for those components, okay? And I'm sure that you can see we're going to have to do some type of trigonometry here. If we have some angle theta, we're going to have to use trigonometry to find those two vectors. And it's pretty similar to when we were finding velocity components in projectile motion. Okay, we just use our sine and cosine functions to then find our force components. Okay, but right now I just want us to focus on how we draw these components and what force diagrams should look like. Okay, and what they can do for us and how they can simplify a scenario. Instead of looking at something that has vectors going all which way, we can simplify them down and adjust the x and the y directions. All right, I finally got through this. I think I probably did this screencast about 10 times. I either had people that were coming in the room or I messed up, which that never happens. I'm kidding. I'm not perfect. But I hope this helped. If you have any questions, come talk to me or Mr. Clausen. And feel free to watch this screencast as many times as you want, because you could revise some notes from it. You can just watch it to understand a little section better. Okay, so keep plugging away. Force diagrams are really helpful, and this is not going to be the first time you see them. Have a good day.